This is an additional video for the section in the calculus book about work. We probably went over it together in class, but just in case you needed a refresher, I thought this problem was a little harder than the majority of them in this section. Okay, so in this problem we have a tank of some sort, and we're considering like how much energy or work. Remember, energy and work both have the same units in this section. They're in English, so the English unit for energy or work is foot-pounds. And if you're doing it metrically, like if you're doing it in physics, pretty much, you can be in joules, right? Anyway, so we have a spherical tank that has oil in it this time, and it says that the spherical tank has a radius of 8 feet. So let's look at the geometry of the situation. So this is 3 dimensions, right? So we have the x-axis kind of going right here. Whoa, that's pretty sloppy. Let's try to make it a little bit straighter. So the x-axis is right here. You have the y-axis like this, and I guess in this case we'd kind of imagine the z-axis kind of coming out at us. But anyway, we're not really going to have to think about the z-axis, so let's just kind of erase that. But it is three-dimensional. All right. So it says that the radius of this sphere is 8 feet, so you can see that it goes out 8 in this way and that way, and it's 16 high. It looks like it's just kind of sitting on the xz plane. Can you see that, how it's kind of sitting on this xz plane? Maybe I'll put z in there in yellow just so we can kind of have a nice reference. Okay, so the sphere is sitting on the xz plane. It doesn't go below it. So that's why it's 16 tall. Anyway, so it says it's half full of oil, so we've got exactly half of that sphere full of oil. And the oil, it gives us a weight, so that's a member of force. So it says it's 50 pounds per cubic foot. And we're supposed to figure out how much work, so find the work, what is that, to pump that oil all the way up through the top of the tank, okay? So first, I think what we're going to have to do is, I like this, it says, consider the oil to be subdivided into discs. This is really, really key. We're thinking about discs of oil because depending on where an individual disc of oil is, I'm going to do it in red because they've kind of got a disc in red. Can you see their disc here? Their disc of oil. Depending on how far down that is and at what position in the sphere it is, the disc is going to have more or less oil, and it's also going to be a variable distance as to the ones at the bottom are going to have to go farther up, so they'll require more work. The ones at the top, even though they're bigger, won't require as much work in terms of because they're closer to the top. Okay? So anyway, we want to think about those discs individually. So let's look at those discs. So the weight is uniform for the oil, 50 pounds per cubic foot, and we've got to think about how much volume that is. But notice, we're doing it like one little piece at a time, one disc, one increment at a time. So we're thinking of a disc like our disc right here that has a delta y. Wow, that's amazing that I got it so small. A delta y thickness, so that's like the height of that disk or the thickness of that disk. And of course it's pi x squared for the area, so pi x squared for the area times the little bit of thickness that it has. And that's the volume of an individual disk. Why is it pi x squared and not pi y squared? Well, look at the geometry. Doesn't x come out this way? So it is pi x squared, isn't it? So we've got a dy times a pi x squared that gives us the volume, and then we multiply by 50, and that'll give us like how much force it takes for each to move each disk up through the top. Then we're going to have to think about how far. But anyway, we've got x's and y's. We don't want both, so use the geometry, and it looks like we're going to solve for y because we're going to want to integrate from like some kind of y distance here, okay? So think about the sphere, at least the x, y slice of that sphere. So you get x squared because it's centered on the x-axis, and then for the y-axis, the center of the sphere is up about right here, right, at 8. So that's where this minus 8 came from. It's been shifted up 8, and the radius is also 8, so 8 squared. Okay, so then you can see that we just subtract that term to the other side and distribute. Looks like they went like this, minus y minus 8 squared, and expanded that out and got this. So now they're going to substitute this x squared right into there. So that's what you get when you do that. So you get that an increment of work is going to be an increment of force. And then we also need to think about how high it's going to be. So remember, these disks are variable height, like I said before. So some of them need to move farther. The ones on the bottom are going to need to move the farthest. How do you know how far? So let's just look at this one. I'll do it in green, where I have this red disk centered right here. How far up is it going to have to go? Well, it's going to have to go about from, if we imagine that's the center of the disk, it's going to have to go all the way up here. Not quite 16, but 16 minus this little distance, and that is just how high it is already, right? So that's just 16 minus y. So that's how far each disk is going to have to move, 16 minus y. And I think we've done all the hard parts now. So what did we have for the incremental force for our disk? We had 50, and then we had pi, right? And then we had x squared was 16 y minus y squared, right? And then the distance was 16 minus y. So that is how much work you're going to have to do to move one single disk. Of course, we're going to now integrate that from, looks like, well, we're going to have to move each one of these disks, so we're going to have to integrate that from 0 to 8. So y is going to range from 0 to 8. Let's do another color. Wow, lots of colors in this problem. So 0 to 8, this distance right here. Anyway, so the work is going to be the integral 0 to 8, this stuff, dy. And I think I'll just tell you the answer to that. I guess we could go look at the next. So I took it out of the book. So I think this is what we had right here. Then you just expand that out, and the thickness of the disk, delta y, becomes dy in the integral. And then you just do the integration, and you get about 500,000 foot-pounds of work or of energy to move that oil from where it's at right now out the top. So quite a bit of effort needed to do that, quite a bit of energy. Okay, so I hope you found this useful.